Thanks a lot for the invitation, Hannes. I'm really excited to be here. It's a great opportunity to kind of spread the word about what we've been doing lately. So I'm Nick Boffi. I'm an assistant professor at Carnegie Mellon. I'm 50% in the math department and I'm 50% in the machine learning department. I think that pretty accurately kind of represents the style of research that I do, where it's sort of half kind of more fundamental applied mathematical techniques and half kind of core machine learning. So today I'm going to talk about a lot of work we've been engaged in that I think Hannes kind of noticed from a recent paper. So this is concerned with learning an object that we call the flow map. So I like to put kind of a flashy title here, generative modeling with lightning fast inference. One way you can think of this is we're kind of trying to learn generative models that have the expressivity and are kind of based on the same underlying mathematical structure as flows and diffusions, but don't have to integrate an ODE or SDE at all. So we kind of want to get the same sort of accuracy and want to kind of develop these generative models in the same sort of dynamical measure transport paradigm. But we want them to have, in some sense, the efficiency of GANs. So we want to be able to generate samples in one or just a few function evaluations. So this ties into a lot of work that people have probably become aware of recently. So there's related algorithms, consistency models, consistency trajectory models, mean flow, shortcut models, et cetera. And one of our goals in working in this area is to kind of, in some sense, bring a bit of clarity to this field. I think it's been a little bit difficult to track because there's many sort of competing methods that are coming out sort of all at the same time. They all have really, really interesting insight and they all work quite well. And they all feel like they are related, but it wasn't 100% clear what the connection between them was. And one thing that we've done is kind of show that you can arrive at all of these algorithms from the same sort of underlying mathematical framework. And by choosing different characterizations of this object called the flow map, you arrive at these existing algorithms. And then you can use that to kind of design new algorithms with improved empirical performance. So I'm going to highlight actually more than just the single paper that Hannes advertised, but some other papers that have come actually before and since the publication of that NeurIPS paper. Okay, so let's kind of jump right in. Let's start with, she can't find my cursor right now. 1 second. There we go. Okay, so let's start with a bit of background. So, I mean, maybe for this crowd, it's not like 100% necessary to motivate generative models, but I'm just going to get rid of this thing here. But let's do it anyway. So at this point, I think we've now kind of all seen some pretty amazing successes of generative AI across domains. So we kind of maybe all were first brought onto the scene with the advent of these sort of amazing text-to-image models like Stability or like Stable Diffusion out of Stability AI, or more recently Flux 3.0 out of Black Forest Labs Flux. So this is a picture of two bugs having a tea party. This comes from a caption where you ask it to generate an image of two bugs enjoying some tea. And it's at this point, I think like we're sort of used to seeing images like this, but it's always worthwhile to pause for a moment and reflect on how it's completely ridiculous that we now have models that can take text as input and generate something like this. Of course, Meta extended this to movies, so they have this amazing Meta movie gen model based on flow matching, where it generates kind of like completely coherent movies. So if you go on their website, you'll find that this is actually a continuous, like 1 minute long movie of this little otter kind of floating downstream, which is perhaps even more mind-blowing than static images. One thing you could argue is that maybe generating images and generating video is in some sense amazing and super cool, but kind of a demo. But more recently, this has of course been extended to interesting scientific domains where we can really start to see how this could dramatically impact the public. So kind of a remarkable example of this is DeepMind's AlphaFold 3, which is a diffusion model that can generate candidate protein structures. And similarly, Microsoft recently released Microsoft MatterGen, which is a diffusion-based model for generating material structures. And these can now be used to kind of search over these complex design spaces with the hope of finding new materials with advanced properties or designing new drugs. And of course, Hannes and Gabriele have also introduced some amazing models as well, like Boltz-2 for molecular design. So if you look at kind of the history of generative modeling, I would argue that there's kind of one fundamental idea that has sort of emerged in recent years. So to see this, we can kind of first instantiate the generative modeling problem in a very kind of simple, abstract mathematical form. It's actually kind of surprising how easy it is to state this problem. So the assumption is that I'm given a data set of examples. Let's call them xi1, where I runs from 1 to n, from a target distribution that I will call rho 1. So it'll be clear in just a moment why I'm using this notation xi1 and n rho 1. Okay, my goal is to draw a new sample. Let's call it x hat 1 from this sample rho 1. Okay, so let's kind of look at the history of generative modeling to see how we sort of gotten to the point where we are now. So the first time I really became aware of generative models was with the advent of GANs, say in around 2014. And at the time, people developed these models and they were able to generate faces like are shown on the right. This was like completely mind-blowing. There was this website, thispersondoesnotexist.com. I still remember like the first talk that I went to on generative AI at MIT, where I saw these kind of example faces being generated, and I was sort of mind blown that this was possible at all. So the way GANs work is they kind of pit two models against each other in this kind of min-max optimization problem. But at the end of the day, you train a model that just takes some random noise as input, and from that random noise, in one neural function evaluation, produces an output sample. Okay, so the training is quite difficult, and it was quite hard to get models that perform as well as the models that we have at scale today. But the inference is incredibly efficient. You just evaluate a model one time. Okay, and this is a point that I want to return to as we start to introduce the kind of more general models that we see today. At some point, people realized that maybe generating in one step was a bit too hard, and this led to the advent of normalizing flows and then eventually continuous normalizing flows. So people kind of broke down the generation into multiple steps. Continuous normalizing flows take an infinite limit and arrive at an ODE that looks a lot like modern flow matching or diffusions. The key difference between modern models is that the training was fundamentally different. Okay, and I'll kind of explain more on this in just a moment. So with the introduction of this idea of breaking down the generation into multiple steps, we were able to improve the quality of generated images, and then we kind of had color examples on CIFAR10 like I'm showing on the right here. Not long after that was the advent of kind of the precursor to modern diffusion models, kind of independently discovered by Jonathan Ho and Yang Song and Erman at the same time. So these models took a similar perspective, breaking down the generation into multiple steps. But importantly, they realized that you can actually break down the learning into multiple steps as well. So continuous normalizing flows kind of learn based only on a loss that depends on the samples generated, while denoising diffusion models somehow have separate losses for each generative step. And this dramatically improved the quality of generated samples. Not long after that, Yang Song realized that actually this process had a limit itself, and then you arrive at a stochastic differential equation, and this led to kind of even further improved generated samples. And then not so long after that was the advent of flow matching, rectified flow, and stochastic interpolants by kind of three groups at the same time. And these approaches now power many of kind of the modern large-scale text-to-image models, video models, and scientific models. So if you look at this chronologically, I would argue that the key idea that has emerged here is that what you sort of need to do to construct an efficient generative model is you want to fix a connection between some simple prior distribution, like a Gaussian, and the target distribution, rho 1, in the space of measures. And then you want to learn to transport measure along that connection. So what these earlier methods, like GANs and continuous normalizing flows, do is they don't fix the connection. Okay, so the connection is kind of free, and the model is simultaneously trying to learn the connection as it is trying to learn to push along that connection. Whereas diffusions and flow matching first fix the connection and then learn kind of the unique velocity field that pushes along that connection. And this dramatically simplifies the problem. It kind of preconditions the learning, and it makes it much easier to learn an effective generative model. So the central question that I want to ask today is it possible to build few-step generative models in this kind of dynamical measure transport paradigm? So can we somehow fix the connection like we do with flow matching, interpolants, and diffusions, but then learn a model that does not correspond to an ODE, does not have to be integrated incrementally, but instead we can kind of just jump in large steps and get to the generated samples much more efficiently? Okay, so here's a quick outline. So what I'm going to do first is I'm going to very quickly introduce stochastic interpolants in case people haven't seen it before, because this is what I'm going to use to actually construct my flow map models. And this is kind of, a very nice way to kind of contain flows and diffusions all in one paradigm. And I'll quickly show that if you use this, you get nice images. And then I'll introduce our new class of flow-based models, flow map-based models, which have significantly accelerated inference. And in fact, I will show you that through the construction of the flow map, we will be able to, in some sense, have the best of both worlds. We will get generative models that have few-step generation, like a GAN, but are based on this dynamical measure transport paradigm. Okay, so let's jump in. So as a quick start, let's kind of give an overview of diffusion models so that I can introduce interpolants shortly after that. Probably most people in the crowd are familiar with diffusions, but we'll just spend a quick minute or so to make sure we're all on the same page. So how do diffusions work? Well, I take some input sample, like this image of this puppy, and then I pass it through some kind of corruption process, like something that converts it just into pure noise. There's many ways that I could try to convert an input sample into pure noise, but one very convenient one is to write down something like a stochastic differential equation. So the way I will describe this is I will say that the change in my sample, dx, is equal to some term that removes the input signal. It makes the dynamics forget about what the initial condition was, and another term that simply adds noise. Okay, and it's possible to show that this dynamics converts any initial condition into just pure Gaussian noise. Then you can ask, well, it's kind of easy to convert signal into noise. The interesting part is converting noise into signal. So is there some way to reverse this process? And in fact, it was shown already in 1982 in a completely different context that a stochastic differential equation like this does, in fact, have a reverse time process. And it depends on this new quantity called the score, grad log rho. Okay. So to connect with this notion I introduced before about how modern models kind of fix this connection in the space of measures, we can observe that when we write down a stochastic differential equation like this, we are defining some kind of dynamical measure transport. In fact, we can say that the time-dependent density of the sample xt, let's call that rho t, it solves a Fokker-Planck equation, which is easy to write down. I've written it here. And this Fokker-Planck equation parameterizes this curve in the space of measures. Okay, so this is an absolutely beautiful idea. And the key observation here is that this kind of breaks the generative problem down into just learning the score. And in fact, I have a different loss for the score at every time. And this makes me able to kind of break down the learning problem across time rather than having to learn an entire velocity field based only on endpoint observations, which is how something like continuous normalizing flows used to work. So it's an absolutely beautiful idea, and it arguably revolutionized the field and maybe even changed the world. I think it goes as far as to say that. But nevertheless, as formulated, there are a few limitations that one might want to avoid. So for example, the base density here must be Gaussian. It's kind of very, very hard to change this forward noising process so it converges to anything other than a Gaussian in a reasonable amount of time. And moreover, this somehow only converges as time goes to infinity. And in practice, this introduces a bias, and I can't really eliminate this bias. This is very much unlike, the finite sample bias that would arise because I only have a finite data set. I don't have access to the population density. This is really specific to the process. And I would like to design an algorithm that does not have this bias built in. In fact, this capital T that appears in the score is precisely the horizon over which I'm going to reverse the dynamics. And the error, the bias introduced is going to be related to what value I take capital T. And so modern implementations often take this to be very, very large to eliminate the bias. They take it to be something like 80 if you follow the EDM guidelines. So what I'm going to show you now is that with a very simple definition, we can actually just eliminate this bias and we can have greater flexibility. In other words, we don't even have to start from a Gaussian. We can start from whatever we want. Okay, so the key definition is the following. Stochastic interpolant is the following stochastic process. I'll call it IT. I take a sample x0 from my prior density. I take a sample x1 from my target density. And I take some optional Gaussian noise z. I take a linear combination of these guys with time-dependent coefficients alpha, beta, and gamma. And x0 and x1 are drawn from some coupling over rho 0 and rho 1. Okay, so they can be paired in some specific way if I know that there's kind of correlations between data from the base and data from the target. I set up this time-dependent linear combination so that it satisfies some boundary conditions. Namely, alpha starts at 1 and ends at 0. Beta starts at 0 and ends at 1. And gamma starts at 0 and ends at 0. Okay, so why is this a useful construction? Well, here are kind of the key properties that actually make this incredibly useful algorithmically. So the first one is that this forms an exact connection between my prior and my target. By definition of my boundary conditions, at time t is equal to 0, I get a sample from rho 0, and at time t is equal to 1, I get a sample from rho 1. So the definition of the interpolant defines a path in the space of measures. Very similar to how when I define a diffusion process, I similarly define a path in the space of measures. It's very easy to sample. So given samples from rho 0 and given samples from rho 1, which I assume I have by construction, then I can just compute IT. It's just this kind of linear combination. It's essentially for free. Okay, and I will actually use this to learn generative models in practice because I will need to be able to evaluate my interpolant to actually estimate expectations to perform the learning. Okay, and last, the base distribution here, rho 0, is completely arbitrary. Can be tuned to rho 1. Okay, so if I have some prior knowledge, in other words, I know something more than just starting from pure Gaussian noise, I can actually build that into the model here, and this can give pretty significant gains in practice. And maybe one comment that's worth mentioning as well is that this includes diffusion as a special case. So in fact, I can take the diffusion process I wrote on the previous slide, solve it analytically, and I will find that this corresponds to a very specific choice of alpha, beta, and gamma with x0 drawn from a Gaussian. Okay, so here's some pictures to make this a bit more concrete. On the first row, I'm showing you kind of a sort of like an image-to-image translation problem where I start from a picture of a white flower, go to a picture of a purple flower with a bit of noise in the middle. You can construct more exotic interpolants that, for example, deform into pure noise in the middle. This is kind of like stitching two diffusion models together exactly on finite time. And the last row is kind of the simplest thing you can do, which just takes a linear interpolation between the data and a Gaussian. And this recovers flow matching and rectified flow. Okay, so how can you use this thing to build a generative model in practice? Well, on the bottom here, I'm showing you a graphical depiction of how this kind of encodes some notion of dynamical measure transport. So here, my base density rho 0 is a two-mode Gaussian mixture. My target density rho 1 is a three-mode Gaussian mixture. And what you can see is that if I look at the time-dependent density, rho t, of the interpolant, somehow it kind of smoothly deforms from the base density into the target density. So this is precisely the dynamical measure transport I mentioned at the start. What I want to do now is actually characterize this dynamical measure transport analytically so that I can convert it into an algorithm that I can learn efficiently. Okay, so we can prove a very simple result, which is that the time-dependent density, rho t, of the interpolant satisfies a transport equation, dt rho t plus div bt rho t equals 0, where bt is the conditional expectation of the time derivative of the interpolant. Okay, so what this equation says is the following. The time-dependent density rho t evolves according to a velocity field b, and this velocity field is constructed by averaging all the velocities of the interpolant. So if I want to understand what the density is going to do at a point x in space, I look at every interpolant that crosses through that point. I look at all of their velocities, or all the slopes of all the interpolants, and I average all of them. Okay? One way you can think of this is that somehow I'm going to recover an ODE here. And when I draw the interpolant, because I randomly pair samples from rho 0 and rho 1, these flow lines cross. For ODEs, flow lines can't cross. And this averaging essentially resolves the contradictions. It kind of makes these flow lines spread apart from each other. So I have a well-defined ODE. Okay, so how do I convert this result into a generative model? Well, the first thing I'm going to point out is that we can efficiently learn this velocity field B. Okay, so B is of the form of a conditional expectation. It's kind of a standard result from statistics and probability theory that conditional expectations are minimizers of square loss regression problems. In fact, you can even take that to be the definition of a conditional expectation. And so it immediately follows that we have a very simple learning objective to estimate this velocity field B. I just take a model, B hat, and I ask it to fit I dot, just in a kind of an L2 least squares sense. Okay, the unique minimizer of this objective will be this target velocity field B. And now, if I learn this thing, where do I get a generative model? Well, it's a very simple result to show that if I look at something called the probability flow equation, or the probability flow ODE, this is just an ODE whose right-hand side is the velocity field from that transport equation, then it satisfies a pretty remarkable property, which is that if I draw an initial condition from rho 0, and I solve this up to time 1, I get a sample from rho 1. In other words, this entire construction reduces the sampling problem to learning the velocity field and then solving an ODE. Okay, it's this second part that I really want to address in this talk. I want to ask, is there a way that I can avoid solving this ODE? Okay, so before we jump into that, let's just kind of highlight that this really works at scale. So here I'm just going to take a very simple interpolant, just a linear interpolant, where I draw my base sample from a Gaussian, and then I draw my target sample from a distribution over images, like on ImageNet 256. Okay, so this really recovers flow matching and rectified flow. We trained this on ImageNet 256 across a range of model scales. Here's some example generated images. And here's some quantitative results. We're comparing here a diffusion transformer to a stochastic interpolant transformer, ranging from 33 million parameters to 675 million parameters. And at every scale, we find that just swapping the diffusion process for this flow matching or stochastic interpolant process reduces the FID fairly significantly. Okay, so this is like a one-line code change, and in practice, you get pretty significant gains. Okay, so that's kind of all the background on interpolants and sort of the setup for how we can build these generative models in practice. And this lets me kind of hone in on the central question that I asked at the start and really convert it into what we can think of as an algorithmic challenge. So the main algorithmic challenge we need to address at this point is, can we avoid that differential equation solve? Somehow we have a very, very nice mathematical framework that we can use to actually build these generative models, but it revolves around actually solving a differential equation. And I want to see if we can stay within that mathematical framework, but not have to solve a differential equation. Can we train a model that somehow gets the solution of that equation, but doesn't have to solve? So if you look in the literature, you'll find that actually there's a ton of interest in doing this. Okay, there's actually a bit of a zoo of existing papers that try to solve precisely this problem. So I would say that the first one that really at least put this on the map in my mind is this paper on consistency models by Yang Song, Prafula Darawal, Mark Chen, and Ilya Sutskever. Consistency models are a beautiful idea, and we'll connect to them at several points throughout this talk. But if you follow the chronology of papers, you'll find that, in fact, they're quite difficult and quite unstable to train. So if you look on the left side of this slide, you'll see that there's several follow-up papers. One is improved techniques for training, and another one is simplifying, stabilizing, and scaling continuous time consistency models. And we will kind of identify this training instability, and we'll show that it's possible to get around it just by defining the objective in a different way. So rather than kind of engineering our way out of it, we'll change the underlying mathematical structure to make the problem better conditioned. It's also very much worth pointing out, on the right-hand side here, there's been very nice lines of extension from people who were not the original authors, including consistency trajectory models, which will look very similar to the models that we'll introduce today. Shortcut models, which recently came out of UC Berkeley. This will be kind of a specific instance of the framework that we introduced today. And then mean flows, which came from my colleagues here at CMU, as well as some collaborators at MIT, which again will kind of be a specific case of the framework that we introduced today. And I should say that all of these works are really inspiring and pretty amazing. So I think all of this is really great stuff. What we've tried to do is bring a little bit of clarity and show that these methods are related to each other. But I think everyone has been really doing some very nice work to kind of contribute to our understanding of this field. Okay, so how can we address this algorithmic challenge, and how can we kind of make progress towards this ultimate goal? Well, I would argue that we can shift to kind of a different paradigm, which is to estimate this object called the flow map. So what is the flow map? Well, the flow map is this object, I'll call it capital XST, which satisfies XST of XS is equal to XT, where XT is any solution of the probability flow. Okay, so this means that the flow map jumps along trajectories of the probability flow. We can picture this graphically here. So here's kind of our picture of the stochastic interpolant from before. Typically, we would kind of move from the left to the right incrementally by solving a differential equation. If we had access to the flow map, then we'd be able to just take steps of arbitrary size. So we can just jump, right? We can jump to time s, we can jump from there to time tau, we could even jump all the way to the end. We can even jump backwards if we want to. Okay. We can note that this object is well-defined. So this is not just some thing that we write down that we hope exists. It really is well-defined. It's precisely the solution operator of the flow. So people have heard of, for example, neural operators in kind of scientific machine learning. This is very related. In a sense, the flow map is a neural operator for a flow or a diffusion-based model. Okay. What I'm going to show you is that, in fact, we can kind of characterize this object mathematically quite well. And this will lead to a number of algorithms for training it. And in fact, if you tune these algorithms correctly, you really do not incur much computational overhead for learning the flow map at all relative to standard flow training. And I think that it's quite possible that flow maps will kind of just replace flows and diffusions in coming years. I mean, you just, for essentially the same training cost, end up with a generative model that can be orders of magnitude more efficient at inference time. And there will also be some very fun games that we can play with this, for example, guidance and inference time steering. Okay, so how can we learn this guy? Well, I'm an applied mathematician, and so when I want to learn a new object, what I typically like to do is characterize it mathematically and try to understand if any of these characterizations can be converted into an efficient algorithm. So let's try to do this. Let's try to write down the fundamental properties of the flow map that we could actually use to learn it. So the first one I'm going to write down is kind of trivial. It's called the semigroup property. It just says the following. If I compose the map going from time s to time u, and then go from time u to time t, it's the same as just going from time s to time t. Okay, in other words, composing two jumps is equivalent to one larger jump. Okay, the proof is kind of obvious. By the way, we've defined the map. If you jump twice, it's the same as taking one bigger jump. But in fact, this idea will come up multiple times, so we'll sort of use it repeatedly. Okay, so let's remember that this is called the semigroup property. Now I'm going to introduce another property, which is not at all as obvious. Okay, this one is called the Eulerian characterization. Okay, so you can prove that the flow map is the unique solution of the following so-called Eulerian equation. This is a partial differential equation defined for every x in Rd and s in t on the unit square. It takes the derivative with respect to s the first time of the flow map, and then it has this kind of Jacobian vector product between the flow map and b, the flow that defines the probability flow equation. Okay, how do we arrive at this equation? Well, we again kind of take this fundamental jump condition, and we just take time derivatives of both sides with respect to s. Okay, my claim is that, in fact, you can show this is also the limit of this kind of interesting application of the semigroup property. I first jump from s to s plus delta s. There's actually a typo there where there's kind of, in the second application, there's an extra s. So I first jump from s to s plus delta s. And then in the second application, I jump from s plus delta s to t. So this is what it should look like. What I'm asking with this Eulerian equation is that if I take one big jump from s to t, it's the same as if I had taken a slightly smaller, an infinitesimally smaller jump from s plus delta s to t. Okay, so we just had two characterizations. One where I kind of take two macroscopic jumps. This one I take an infinitesimal jump and then a macroscopic jump. You can imagine that there's probably one more where I take a macroscopic jump and then an infinitesimal jump. And this leads to the so-called Lagrangian characterization. Okay, so this is a completely different characterization. This is no longer a partial differential equation. This says that the flow map satisfies this kind of infinite system of ordinary differential equations. One way that you can understand this Lagrangian equation is really that the flow map itself solves the probability flow ODE. This is very intuitive because the flow map is giving you trajectories of the probability flow ODE, so they must also satisfy the probability flow ODE. Okay, and the proof here is essentially the same. I just take a time derivative with respect to t of both sides of that jump condition, and I apply the fact that xt solves the probability flow. And my claim is that very similar to the Eulerian characterization, I can kind of write this down in terms of an infinitesimal semigroup condition. Namely, what I do is I first jump from xs to xt minus delta t, and then I jump from xt minus delta t to xt, and I ask that that's the same as if I had just jumped from xs to xt. Okay, and the key here is that somehow when I do it this way, I don't get that spatial Jacobian. I do not have the grad x appearing in the equation. This grad x is actually going to be the source of optimization difficulties that have appeared in consistency maps. Okay, so now that we have these characterizations, let's observe the following, which is that if I have a pre-trained flow, let's call it b hat, then I can use these characterizations to distill it into a flow map. Okay, so here's a theorem, which leads to an algorithm that we call Lagrangian distillation. So if I want the flow map of a pre-trained probability flow ODE, well then all I have to do is look at the square residual on that Lagrangian equation and just minimize it. And in fact, I can minimize it over the interpolant because the interpolant gives me access to the density that's produced by the original model. Or if I haven't learned the model perfectly, then the difference between the interpolant density and the model density is kind of minimal. So I can distill just by imposing that my candidate flow map solves the flow that I have pre-trained. So one way you can view this is that my pre-trained flow model is a teacher and my flow map is a student. Okay, so you can show that the unique minimizer of this objective is precisely the flow map. And in fact, you can show something a little bit stronger, which is that you get a guarantee in Wasserstein. So in fact, this objective upper bounds the Wasserstein error between the density produced by my pre-trained model and the density produced by my flow map. So in other words, as I minimize this objective, I systematically reduce the error and I get closer and closer to recovering the original model. Okay, so similarly, I can write down kind of a dual algorithm to the Lagrangian algorithm I just wrote down, which is the so-called Eulerian distillation algorithm. And here I just play the same game. Okay, I just minimize the square residual of the Eulerian equation in expectation under the interpolant. And again, I'm viewing my b hat as my pre-trained teacher and my flow map as my student. And I have a very similar guarantee in Wasserstein. So both of these are kind of theoretically justified. And when I minimize either of these objectives, I systematically reduce the error of the flow map model. And in fact, this approach here recovers the original consistency distillation algorithm introduced by Yang-Song. I should mention that NVIDIA, in particular, Amir Sabor, Sanja Fidler, and Karsten Kreis, recently released a very, very nice paper that they call Align Your Flow, which is intimately related to this Eulerian objective. So if you look in the appendix of our recent paper, we kind of form a connection to this. So if you pick a very specific parameterization for the flow map, and you kind of engineer the objective in a certain way, then you recover this Align Your Flow distillation algorithm. This was recently tested at very large scale by NVIDIA, and the results are kind of remarkable in my mind. So they were able to distill Black Forest Labs Flux into a 4-step model. So they have this kind of 4-step text-to-image model. Here are some of the images shown on the left here. So this is like, yeah.
What is the status of distillation versus training from scratch with these types of models?
Yeah, so that's a great question. So the next thing I'm going to discuss is precisely training from scratch. So I mean, I think it really depends a little bit on like what your end goal is. So distillation algorithms are super useful if you're thinking like someone shipped you a large pre-trained model, and perhaps maybe you can't even train that model on your own. So NVIDIA can train whatever model they want. You know, they're the most GPU-rich people in the world. But for example, like I could not train Black Forest Labs Flux. I just don't have the compute to train such a model. But Flux is open source. And actually in this paper, NVIDIA showed that you can distill Flux in 8 hours on a single A100 node using a LoRa. And these results come from LoRa distillation. So that's kind of amazing. So it basically says that distillation may enable you to kind of approach larger scales than you would be able to access training from scratch. And you can kind of repurpose large open source models. However, one reason you may not like distillation is because if you want to build your own model, it's just kind of annoying that it splits the training into these two phases. You need to at some point like decide when are you going to stop training the flow, when are you going to convert it into a flow map, and the conversion will almost certainly be lossy. So like in the distillation phase, the best the model can do is replicate the performance of the teacher. It's like not possible to do any better. And just information theoretically, I mean, you're probably not going to get the loss exactly to 0. And so you're going to get a model that's kind of worse than the original teacher. So what we would like to do is kind of develop a paradigm where if you have the compute for it and you want to train a large model, you can just run the algorithm for as long as you can afford, and you just keep getting a better and better model out of that. So yeah, I would argue that they kind of serve different purposes, and they're both useful, and there's impressive results with both of them. Okay, so that's actually... Sorry, did that answer your question, Hannes?
Yep. Just saying, okay.
Cool. Okay, so that's a great segue into the next section, which is direct training. Can we actually learn this flow map directly? Okay, so the key behind this whole interpolant framework is that we kind of like target this velocity field in a very specific way. We're able to characterize it as a conditional expectation, and then we kind of know exactly how to learn that conditional expectation. And then similarly with distillation, if we have this pre-trained model, we kind of know that we just need to minimize the residual on one of these equations, and then we can recover the flow map. But if you want to do direct training, the issue is that it's not really obvious at all what the signal should be to learn the flow map. It's this like complex nonlinear operator. It's not related to some conditional expectation. It's just not really clear how to do this. So one idea that we had is perhaps to relate it to training of flows. So you can in fact prove a very simple identity that we call the tangent identity, which says the following. There's this interesting kind of limiting derivative. I take the derivative with respect to time of the flow map, and then I take the limit as s goes to t, and I recover the flow bt. Okay, so this is actually kind of a very simple result. It's not hard to prove at all, but it's very subtle what it actually means. Okay, so in a sense, it reveals that inside the flow map, there is an implicit flow. So if you have a flow map, then you have a flow. And this perhaps should not be so surprising because the flow map is jumping along trajectories of the flow. And so if I just take a really, really small jump, then I should be able to recover the flow from that. Okay, when we first wrote this down, it wasn't entirely obvious what to do with it, but it felt like it should be possible somehow to use this to design an algorithm. Okay, so the first thing I want to do is show you that in fact, with a specific useful parameterization, we can eliminate this kind of strange limiting derivative and just get a very, very simple way to evaluate the implicit flow. So if we use this parameterization that kind of looks like a big Euler step, where now I'm going to parameterize VST as my model, but then if you just calculate this derivative and take the limit, you just turn the crank a little bit, then you find that VTT is actually equal to BT. Okay, so the implicit flow is actually very direct. It's just V evaluated on the diagonal, S is equal to T. Okay, so here's one way that we can kind of graphically picture this. So on the left-hand side here, I'm showing you the tangent condition. It just says that when I take smaller and smaller steps, at some point, I get access to the tangent to the probability flow trajectories, and that tangent is precisely the velocity field B. And on the right, I'm explaining this kind of Euler step parameterization. So one way you can interpret this object VST, if I take 2 points, XS and XT, on a given trajectory, I draw a secant line between them, then VST is really the slope of that secant line. And then this identity VTT equals BT becomes quite simple, because as I start moving these points so they're right next to each other, the secant line becomes a tangent line, and then I recover the flow, B. Okay, this object VST is precisely what mean flows call the mean flow. Okay, so this relates us to what we like to think of as the self-distillation paradigm. So the core idea is as follows. We're going to introduce this parameterization of the flow map, where now we want to learn V hat. And what we're going to do is we're going to use this implicit flow to train V hat on the diagonal S is equal to T, like it's an interpolant model or a flow matching model. And then we will distill this implicit flow on the off diagonal for S not equal to T. So here's a little diagram that pictures what's going on. So I have my ST plane. ST plane is where I need to learn this object VST. The upper triangle of the ST plane is the generative pathway. This is where S is less than T. This is going forward in time. On the diagonal in green, that's where I have an external teacher signal in terms of flow matching or stochastic interpolants. And on the off diagonal, that is where I know how to distill. And so the idea is that I can construct a so-called self-distillation objective, which is just the sum of these two terms. So that gives me LSD. This first term here, you can see, looks just like we were training stochastic interpolants, except instead of B hat T, it's V hat TT. So it's really just this function on the diagonal. And then I'm going to add this additional distillation term. And the idea is that we can construct 3 options for distillation using Lagrangian, Eulerian, and semigroup properties, these 3 characterizations that I introduced before. And this will recover, as far as I'm aware, every algorithm for training consistency models or flow maps in the literature. Okay, so the first one is so-called progressive self-distillation. Let's keep in mind that the self-distillation objective, it's given in the top right. It's the sum of a interpolant or flow matching term and a distillation term. So we'll introduce one distillation term, which is called progressive self-distillation. This just says that if I take 2 smaller steps, it should be the same as 1 bigger step. It's literally just imposing the semigroup property. Okay, and you can prove that the unique minimizer over V hat is the flow map. I'm going to show you some experiments where we test drawing this point U in between uniformly between S and T, or taking it to be a Dirac centered at S plus T over 2. Okay, so this approach, if you massage the objective function a bit, and then you discretize in time, recovers shortcut models as introduced by this Franz paper at iClear 2025. Similarly, we can introduce a so-called Eulerian self-distillation objective. So here, I just ask that my flow map solves this kind of implicit Eulerian equation, where now I have V hat SS appearing where my pre-trained flow BSS appeared before. Okay, so now it's just the Eulerian equation for the flow that's defined implicitly by the map. Okay, and remember that you should think of this as a limit of a kind of certain semigroup condition where I'm asking that XS and XS plus delta S jump to the same point. Again, you can prove that the unique minimizer is the flow map. And this is precisely the objective function that is used by mean flows and is used by Yang Song for consistency training in 2023. In the appendix of our paper, we give an exact mapping between all these algorithms in this approach here. And in this case, we can kind of port over some of the machinery from our distillation algorithms and show that, in fact, you get a bound in Wasserstein when running this algorithm. Hey, one thing I want to point out is that this spatial Jacobian appears. This is actually going to be a problem. Okay, and then last is the Lagrangian approach, which is what, in fact, we have a special place in our heart for because we find that this performs the best across many different modalities. So here we just, again, play the same game. Now we impose that the flow map solves this Lagrangian equation, where the Lagrangian equation is coming implicitly from the flow itself. And again, graphically, you can think of this as taking one big step and then one infinitesimal step. And again, the unique minimizer is the flow map, and we have a guarantee that minimizing this objective reduces the error. I will point out that there is no such guarantee for progressive self-distillation or for shortcut models, and I believe that that is fundamental, actually. I think that you cannot prove such a guarantee. I'm happy to give more details on that later. Okay, so I want to introduce one kind of very important engineering detail. It's not even clear it's an engineering detail or if it's really kind of fundamental and goes beyond that. So here's our kind of training picture. We have this ST plane. We have direct training on the diagonal. We have distillation on the off diagonal. You should have some intuition that somehow signals should only flow from the diagonal to the off diagonal. We have this kind of external teacher signal on the diagonal where we're getting observations of the interpolant. And then we're doing this implicit distillation on the off diagonal. So we want to make sure that the flow map kind of learns from the implicit flow, and that the implicit flow does not learn to match the incorrect flow map. We really want to kind of keep this sort of teacher-student paradigm that appears naturally in distillation. So in practice, we can implement this using something called a stop grad. So what we do is we just place a stop gradient operator anywhere the implicit flow v hat appears. And this makes sure that we kind of get this teacher signal flowing to the student flow map. Okay, and this actually is essentially necessary. It really doesn't work very well at all if you don't do this. Okay, so that's a bunch of math. Let's start showing some results. So first thing I want to show is kind of this low-dimensional checker data set. I really like this data set because it's easy to run, lets you debug your algorithms, and you can see things very nicely. So here I'm comparing Lagrangian self-distillation, or LSD, Eulerian self-distillation, or ESD, progressive self-distillation, or PSD, in the two configurations. PSD-M is where I draw that midpoint. PSD-U is where I sample it uniformly. Okay, I'm showing you a single evaluation as well as 8 evaluations. What you see qualitatively is that Lagrangian kind of appears to produce the best results. Certainly for one step, the boundaries are much fuzzier for the 3 other algorithms. And in fact, if you quantify this, for example, by computing a KL divergence, you find that you get the best results with Lagrangian across essentially all step counts that we tried. For 16 steps, everybody's kind of pretty equivalent and everybody kind of nails this. Okay, this is sort of a trivial system. We can kind of extend it now to more interesting cases. So first thing we did was go to CFAR10. It turns out that CFAR10 gives you some interesting insight into training dynamics. So on the right here, I'm showing the parameter gradient norm as a function of the training step for these 4 different algorithms. And what you see is that the Eulerian self-distillation algorithm kind of blows up very immediately. In fact, it becomes incredibly unstable. The parameter gradient norm goes kind of haywire. And this appears to be due to the presence of this spatial Jacobian term. Okay, and if you actually go and you track the existing methods that use this approach, like consistency training, mean flow, consistency trajectory training, et cetera, they really put in a lot of work to try to stabilize this term. You actually have to be very, very careful about how you train this term. Otherwise, everything just sort of blows up. That's why we saw that there were kind of 3 papers from Yang Song and collaborators on actually stabilizing consistency training. Okay, so this is kind of an open question, which is interesting. Why is this so unstable? It's really not clear, and it appears to be something sort of fundamental to these large-scale neural network models, that spatial gradient is very, very badly behaved. Okay, so we took a different approach. Rather than kind of engineering this algorithm so that we could actually stabilize this, we asked, is there a way to just change the algorithm so that it remains stable? And in fact, LSD and PSD give us direct ways to do this. So here I'm showing you some image generation on AFHQ. Here I'm quantifying performance in terms of FID across a range of step counts. I want to emphasize that in this paper, we were more going for like conceptual and methodological development. So these FID scores are not state of the art. They're respectable, but they're not state of the art. We are in the process of writing a follow-up paper where we have near state of the art performance on high resolution data sets like ImageNet 256 with Lagrangian. So you can stay tuned for that. That's a collaboration with Eric and Michael Albergo and several others. So here I'm just showing you qualitatively and quantitatively how these algorithms do. And we kind of find very similar to the checker data set that Lagrangian approaches work the best. And then we also verified this as well on Celeb 64, where we saw essentially the same trend, that somehow Lagrangian across all step counts attains the best performance. Okay, so I want to take maybe 5 minutes to just show that we can do some pretty fun things with flow maps that actually go beyond just accelerating the inference time speed. Okay, so one thing I want to point out is that we can play very interesting games with inference time controllability and reward guidance. Okay, so this is a paper I actually think it's not in the archive yet, but should be imminently. So here's the idea. So let's say we have access to a flow model, x dot t is equal to bt. And let's say we want to sample from the reward tilted measure, e to the r rho 1. This is kind of the standard fine-tuning setup, where I want to get samples that are high quality as measured by some reward model. Okay, there's many approaches that just do something totally ad hoc, and they just modify the generative process to involve the gradient of the reward. The issue with this is that, well, one, it's totally ad hoc. It's not clear it makes sense, but we'll just punt on that. We'll just use it. But another issue is that the reward is really only defined at the endpoint. It's only defined at time t is equal to 1. And so the way people actually handle this in practice is they use this denoiser function, the conditional expectation of x1 given xt. But this is a very bad approximation of the endpoint of the trajectory. Okay, so what we propose is to use something called the flow map look ahead. So we just use our flow map to jump to the endpoint of this trajectory. So here's a picture to kind of keep in mind what we're doing. In fact, I've simplified the setup fairly significantly here. We actually have kind of an interesting stochastic formulation that lets us play fun games with resampling and things like that. I've just specified it in the deterministic context to make it match the rest of the talk. But what we're doing is we're kind of guiding these trajectories by jumping to the end, checking the reward to see what they are, and using that to adjust the generative process. Okay, what we did was we applied this for image generation at large scale using that pre-trained 4-step flow map that was distilled from Black Forest Labs Flux by NVIDIA. And we use a reward model that comes from a VLM, a vision language model. So one thing we first tested was if we can use this approach to improve prompt adherence. So here we have a prompt, which is an analog clock showing exactly 4:45. If you run this through ChatGPT or Gemini Nano Banana, for example, you will find that it produces a clock, but it's not at the right time. If we use this flow map look ahead, then we can actually get this to sort of work exactly. On the right-hand side here, you can see that we're generating these clocks that are essentially precisely at 4:45. And this really just comes from having this improved approximation capability of jumping to the endpoint. We can kind of play other fun games. So on the left here, I'm showing you another example of this, where the prompt is a man reading a book that shows a picture of the same man reading the same book. So if you run this through Flux, you'll get a man reading a book, and sometimes there's a man on that book or in that book, but it's not the same man. If you run this with the denoiser algorithm that I mentioned people typically do in practice, then you'll get a picture of a guy reading a book, which typically has a picture of a guy, but it's not the same guy. If you run our trajectory tilting algorithm, where we use this more exact look ahead, then it essentially works every time. So in the bottom row on the left, you can see that it really is the same guy on the cover of the book and reading the book. And on the right is kind of a similar example where we ask for a bicycle with square wheels. And in most cases, if you just run a model on its own, it actually just produces a bike that doesn't have square wheels. The denoiser gets it sometimes, but not always. And our algorithm gets it every time. And last, we can kind of play with fun applications like style adherence. So here we give it a reference image, which is this kind of like angry looking mushroom with a weird little like looking glass. And then we gave a prompt, which is a cute, grumpy cartoon mushroom character walking his dog. And we want the model to generate a picture that satisfies the prompt, but is kind of in the style of the reference image. So in the middle, we're showing results generated by Flux1 dev. You do this, you get a cute, grumpy mushroom character walking his dog, but it's not the same mushroom. You run our algorithm on the right, you get the same mushroom. And I'm quite excited about what we can do with these kind of steerability algorithms for other applications, kind of going beyond things like prompt adherence, but actually using this for design problems like molecular design. Okay, so I'm probably running out of time now. I guess it's 12:55. When should I wrap up? Should I call it now, Hannes, or should I give 2 more minutes of
Yeah,
results?
I think it would be nice if we could have some questions now. I would definitely be curious to ask some questions if you're happy with
Yeah.
that.
Okay. Yeah. So let's just wrap up then. Let me just quickly say that this all extends to the kind of Riemannian context where you have data that lives on manifolds. So for example, if you want to generate protein backbones, or you want to generate molecular structures where you need to generate torsion angles that live on some kind of torus. And in fact, we recently extended this to this setting. And you just need to use a bit of Riemannian geometry, basically. So you can define a similar kind of geometric flow map that has a kind of analogous Euler step parameterization, but it uses the exponential map instead of taking this kind of linear Euler step. And there's an added advantage in this kind of geometric context, which is that taking fewer steps doesn't just let you evaluate the model less, but it lets you avoid the kind of expensive manifold projection that often has to be used to enforce that your generated samples actually satisfy the manifold constraints. Okay, and there's some details here, but we can skip over them. Okay, so let me just give a call out to my good friends and collaborators. All this work was done with many different people over a long period of time. In particular, Michael Albergo, Eric van den Eyden, Saining Zia, Yifan Chen, Willis Ma, Mark Goldstein, and then more recently, Carles Domingo Enrich, Carson Kreis, Joey Bose, Amir Sabor, Sandra Fiedler, and Oscar Davis. Okay, these are all really fantastic collaborators, and it would not have been possible to do any of this without the hard work from them. Awesome. Well, thanks again for inviting. Thanks for listening, and I'm happy to take any questions.
All right, thanks for the nice presentation. Then I would quickly like to sort of should I no longer care about any of the distillation map papers that are coming out, because I can now, I should now just go ahead and try to have sort of this, let's call it framework, and just put it into this framework, and it should essentially be the same. Okay, this question.
So are you asking specifically about distillation, or are you asking for like other works related to consistency models and things like that?
Maybe you can go through your slides quickly where you have all of your different objectives now, so to say.
Yeah, yeah. So for direct training or for distillation? Let's do direct training.
Yeah.
Yeah.
So this is sort of the 2 steps should be the same as 1 step
Yeah.
training, right? Then
Yeah.
we also have this one, Eulerian. What was the intuition behind that one?
Yeah, so yeah, let me just go through them maybe slowly. So this one is, as you said, 2 steps should be the same as 1 step. This recovers shortcut models. So this idea kind of appeared a little bit before we wrote the paper, but we have kind of a more broad, slightly more general picture. And one kind of issue that arises with this approach is that because you're composing the map twice, you're kind of bootstrapping smaller steps to larger steps. And in practice, it's hard to recover from this bootstrapping. So there's kind of like distribution shift that this introduces. And this is really why you kind of can't prove anything theoretically about this algorithm. And I think it actually introduces a pretty significant performance hit in practice. But one thing that is nice about it is that you don't need to take any derivatives of the map. So it really just relies on evaluations. You don't need a derivative with respect to time or a derivative with respect to space. And there may be situations where either of those derivatives are badly behaved, and then this would be kind of the right algorithm to use. Another approach is the Eulerian. So here the intuition is this picture that I drew at the bottom. You ask that 2 points that are kind of infinitesimally spaced apart at the start end at the same location. And this recovers consistency training, consistency trajectory model training, mean flow, align your flow. This, I would actually say the vast majority of papers that train flow maps or consistency models, they do so via some version of this. They don't always present it in that way, but you can almost always massage it into this form. And we do this in the appendix if people are interested. So this
We're
works very well.
We're
Sorry?
saying that the direction that we would go in when going from S to T should be the same as the gradient of, yeah, what is the second thing?
Yeah, I'm not sure it's so easy to interpret it in that way. So I think the right way to think about this is basically you're asking, like, let's say I want to consider where a point will jump. That's what this IS is. So that's some starting point. And now I want to ask, how would where that point goes change if I perturb the starting time a little bit? So I'm starting from the same point, but instead of starting at S, I'm going to start at a slightly different time. And the answer
Ah,
is that it advects. So it's like it advects along the flow of a fluid, and that's precisely what this grad X times V term is encoding.
okay. Then let's just go through all these raised hands. I'm seeing that there's quite some interest.
Yeah,
Onion.
sure. I actually cannot see the Zoom, so if you want to handle that,
Yep.
that would be great.
Yeah,
Of
can you
course.
hear me?
Yep,
Yeah.
let's go.
Yeah. Thank you for the great talk, and yeah, it's really nice to see everything coming together in your this incredible framework. So I have question about first a clarification. So what this flow map will give me is a one-step generation, is what this framework is promising. Is that correct? Or in
Yeah, so it's actually like it's more general than that. So it lets you jump from S to T in one evaluation. So in particular, if you set S is equal to 0 and T is equal to 1, then you get one
Mhm.
step evaluation. But
Okay.
in general, like taking more steps is easier than taking one big step. So you can take two or you can take four, and you'll often find that the performance improves a bit if you allow yourself to take more steps. So it does promise
Okay.
one step generation, but it also promises in some sense like adaptive generation that you can use to sort of tune how accurate you want your samples to be.
Got it. So in this regard, I have one question because I work with using flow matching for image restoration.
Okay.
So at every step, because I solve an OD during inference for the restoration task, at every
Yeah.
step I have the guidance from the condition that I provide to the model during the integration process. And
Yes.
I feel like this might be an intuitive feeling, but correct me if I'm wrong. So at every PT, the model sees the condition and it has been trained in such a way that at every T, the model has the condition. And during solving the OD, also, if you follow the same steps T, and then there is in distribution, and the model kinds of converges into a solution for that restoration, which is consistent, right? But if I train with some T's, a list of T's, and then during generation, the model has to jump between T's only, wouldn't that be a problem? So specifically for restoring scientific images, for example.
So I guess what I would say to this is that it really depends on what exactly you want to do. So one thing we're playing with now is precisely figuring out the right way to use flow maps for guidance. And I think there are kind of interesting algorithms that go beyond what you're saying, like take a big jump and then use a bit of guidance. But
Yeah.
the specific context that you're looking at, we sort of address this in this work here. So you can actually still integrate a flow if that's useful because you have access to a flow through this
Mm-hmm.
implicit VT. And in fact, we
Mm-hmm.
find that when you train the flow map, the implicit flow is typically better than if you had just trained a flow independently. But then now, because you have both the implicit flow and the flow map, you can look ahead. And so you can check where this thing is going to go. So oftentimes for things like image restoration, you might want to
Mm-hmm.
see what is the image I'm going to generate and is it consistent with the rest of the image? And to do that, you need to get to the endpoint. And this is precisely what the flow map lets you do.
Okay. And one last thing about this. So I recently came across a paper from people at Mila, if I'm not mistaken. It's called that incremental generation is necessity and sufficient for universality in flow-based modeling. So they say that the more incremental steps you do, the better your flow model kinds of produces the output. So I'm not
Mhm.
sure if you have looked at that paper, but yeah, so that kind of reinforced that fact inside me that yeah, this number of iteration steps that we do during the solving of the ODE is actually very important. At least for my task was my understanding. But yeah.
Yeah, so I haven't looked at that paper specifically, so I can't say. I mean, one thing that I actually usually say when I give this talk, which I didn't at the start, is that you should be skeptical a little bit that this is possible because somehow it does feel like it's more powerful to take incremental steps. But we find empirically that it is possible to do it in one step. Like somehow you can get basically the same results in just one or a few steps. But nevertheless, there is no question that if you allow yourself to evaluate the model more, then you are somehow gaining expressivity because you're basically like increasing the depth of the model. And I think ultimately, how few of steps you can get away with is going to be dependent on the specific application. So it could be true that for like some of these scientific problems where maybe you need extremely high resolution in some PDE context or something like this, like you really need to take incremental steps. Certainly for image generation and for molecule generation, we have found that this is not the case. You can actually just take 1 to 4 steps and you get very good results.
Got it. Thank you very much.
Yeah, thanks for the question.
Hi.
Then sounds good.
Thank you for the talk. I'm wondering, do flow maps also give you like density estimation and then or like log p and then therefore like policy gradient type methods?
Yeah, so great question. The form I presented here, no. But we have another follow-up paper that I didn't have time to discuss where you can view the coupled sampling and log p system as one bigger ODE, just in d plus 1 dimensions. And then you can learn the flow map for this coupled system. And now you do have likelihood. So we just wrote a paper in collaboration with some people at CMU, Max Sinchowitz, Zico Coulter, Russ Kudinov, et cetera. And we are indeed now looking at a follow-up where you can do policy gradient. So these are things that we're actively thinking about. And very forward-looking of you to ask this question.
Thank you.
Is that d plus 1 dimensional ODE equivalent to the likelihood computation from the score-based generative modeling paper, or from continuous normalizing flow where you solve the likelihood? Okay.
Yeah, it's the same thing, except now you just view it as a slightly bigger ODE and just learn the flow map for the bigger thing. And then all these losses go through in this setup as well, but there's kind of coupling between the two dynamics.
I had a question about the grad X term. First, correct me if I'm wrong, is that essentially equivalent to the score? I'm noticing that in the Eulerian form, you're taking the derivative of the beginning, and you get this, I don't know, maybe that's equivalent to reverse time, and you take the derivative, and for Lagrangian, you take the derivative of the end, and you get something that no longer has it in it. Is that equivalent to like reverse time versus forward time, needing the score in one direction but not in the other?
It's an interesting analogy. I do think that it's very much the right way to think about it in terms of like just perturbing the initial point or the end point. But both of these are going either forwards in time or backwards in time. So there's actually no restriction, like t can be bigger than s or it can be less than s. Actually, the way I wrote this loss here, s is less than t, but it doesn't have to be. I can send the second integral to be from 0 to 1. So I don't think there is a mapping between forward time and reverse time. And this grad x actually is different from the score.
So then why does it only show up once? From a, I don't know, is one direction harder than the other in that sense? Or in some sense?
So in some sense, actually, like they're kind of the same equation written in a different form. So the reason we call this the Eulerian equation and the Lagrangian equation, it comes from fluid dynamics. So there's two frames of reference. One is the so-called Eulerian frame, where you're like sitting on the bank of a river and you're watching the fluid flow go by. And the other one is the Lagrangian frame, where you are a particle in the fluid and you're moving with the river. So what you'll notice is that in this equation, I'm evaluating at the interpolant is. That's why we call it the Eulerian equation. But in this equation, the Lagrangian one, I'm evaluating at the flow map. That means that I'm moving with the flow of probability. And so it's really just how are you encoding that things are moving? In Lagrangian, you encode that things are moving by evaluating on the flow map. And in the Eulerian, you encode that things are moving by basically pushing forward the flow map through the velocity field. And that is precisely this grad xv kind of term. But so in theory, they're kind of the same thing. But then in practice, grad x is typically very nasty for large-scale neural networks. So numerically, they behave very differently.
Very nice. And then one more question if people aren't annoyed. Yeah, no, that was a really good explanation. Thanks. Separate question about applying the self-consistency structure to V of t. What does that, or
Not
V?
sure.
Yeah. What does that like do? Oh, I am.
Wait, Nicholas, did you?
Actually,
hello?
Nicholas,
sorry. Somehow on my end, I got muted and I couldn't hear anyone. Could you repeat what you said?
Yeah, that was just really good, real good explanation. That makes a lot of sense. And I had a separate question about VTS. what exactly does applying the semigroup structure do, like from a functional analysis perspective, or interpreting it as like a matrix? Does it do anything interesting linear algebraically? Like what kind of structure does VU22 have when you're extending it in this way to this triangle? Is there like a nice, I don't know, existing name that it lines up with?
Yeah, that is a very good question. I'm really not sure, actually. I don't know.
Then I guess what I'm wondering is if there was a way to parameterize the neural network to enforce this condition with the architecture in the same way that you do
Yeah,
conservativity with
that's a great question.
selecting a gradient.
That's a great question. I have
But
thought about
theoretically, it
this.
wouldn't need the loss.
Yeah, I mean, if you could do that, then it would be a bit of magic because it would basically say, like, just train a flow model on the diagonal, and then you get the flow map for free. Like, you kind of won the game if you successfully. I don't know that it's possible. I mean, at some point, I was discussing with my colleague Albert Gu, the guy who developed state space models and Mamba, et cetera, about if there's a way to do this. We couldn't come up with anything, but we didn't spend forever thinking about it. We only thought about it for a bit. It starts to feel a bit reminiscent of what they used to do with normalizing flows. So in normalizing flows, they had these kind of invertible architectures where you had these like kind of very specific matrix multiplications that made it possible to invert every step. You would kind of need something like that. And then there's a question of like, if you do this, do you somehow lose expressivity in the structure? I think it's a super, super interesting question, but I don't know how to solve it.
Oh, thanks. Great answer.
Hi there. Thank you for the great talk. I had one question about, so basically we're modeling every possible single, like along the probability flow trajectory, we are trying to model every possible time t and s and their jump between them. But inside of the real world, I feel like the most interesting that we care about is about like the data. So I believe if we're trying to model these flow maps, it will be like increasingly difficult, like modeling a consistency model. Do you have any insight on this?
I'm not sure I fully understood the question, actually. So I agree that the flow map is a more complex object than the flow. There's no doubt about that because it needs to integrate the flow, which is why I think like one should approach any of these methods with skepticism about how possible this really is. So for example, you can construct very simple dynamical systems where the flow is kind of trivial, but the map is horrendous. Like the classic example of this is like Lorentz 63 from like chaos theory. It's a three-dimensional dynamical system. The right-hand side is bilinear, so it's like as close as it could possibly get to linear.
Right.
But the map itself is chaotic and essentially probably impossible to learn. So in general, this is very hard. I would say the flow map is like exponentially harder than the flow in the worst case. But then the question is, what actually happens in practice? And what we find happens in practice is that these worst case bounds are not reflective of reality at all. And it very well may be something to do with high dimension. So for example, like if you think about these very, very high dimensional image generation problems, there's somehow like a lot of room in this high dimensional space. So that maybe the flow lines don't have to be so curved, they don't have to be so nasty, and therefore the flow map itself is not that much more complicated than the flow. That is really what we see empirically for many of the tasks that we've actually tried.
Interesting. Thank you for the clarification. Another question that I have in my mind is that you said like the Lagrangian form is better than the Eulerian form. Is this just like an empirically finding, or there's a proof for that?
So this is empirical. Actually, the theory is weaker, interestingly. The theory is stronger for Eulerian, but in practice, we find that it works much better. And again, I think this is it's essentially a numerical thing. It's related to the fact that by construction, the Lagrangian loss does not have a spatial Jacobian. And that spatial Jacobian is really, really unstable to compute over neural networks. And so like people typically introduce clever tricks to avoid it.
Yeah, I see.
Like stop track, things like that. But this just avoids it at a mathematical level. And so it works very well. It's worth mentioning, though, that like, we've done these experiments and we find quite systematically over scientific data sets and image data sets in all of our comparisons that it works the best. but we don't have state-of-the-art results. And state-of-the-art Eulerian results are actually better than the top results that we have. We have ongoing work that is challenging this. We're hoping to put out something soon that shows that we can get state-of-the-art results with Lagrangian. But in our internal comparisons, indeed, we find a quite systematic trend that Lagrangian is just kind of better behaved. So we think it's very exciting and very promising, and you know, we're hopeful that people will find it interesting. We'll try it on their own problems because it seems to be much more stable.
Thank you. Because currently I'm doing is for the distillation kind of work, and I'm trying to apply some of the techniques that you have in your paper to mine, and we focus towards more on like a data-free way to do the distillation. Thank you so much.
Yeah, no problem. Thanks for the interest.
Okay, then I think we have one more hand.
Yeah, thank you for the great presentation. I have a very simple question. Am I right that so far the best recipe for working with flow map and conditioning is not the classifier-free guidance, but essentially the conditioning itself. So we just condition the input on some label and that, right?
You can do classifier-free guidance, actually. I did not discuss it in this talk, but it's in the paper, the 2025 NeurIPS paper. Basically, you can define the classifier-free guided flow, and then you can apply any of these self-distillation objectives to the classifier-free guided flow. And it works very well. So again, in some of our ongoing work where we're scaling this to ImageNet 256, we use classifier-free guidance extensively, and it makes quite a big difference. And you can even train over kind of a range of guidance scales. So you get a flow map that depends on a guidance scale, and you can use it kind of adaptively however you want at inference time.
Okay, so
But
this
is
is only related to distillation, right?
No. This is also for direct training. So the key is that we're doing direct training via distillation. So anything that you can do with distillation, you can just plug in directly to this formalism. That's really, in fact, one of the key points that we're trying to make, which is that when you write it in itself.
Yeah, it's just the vector field that you're using now is the classifier-free guidance vector field.
That's right. But specifically like the implicit classifier-free guidance one. So you take your v hat TT, you construct the CFG field from that, and then you run this on that. Yeah.
But isn't that a problem that for each scale for classifier-free guidance, we have to retrain our model since we construct a classifier-free guidance field for each scale? Or we have some way to avoid that?
No, you don't, right? So let's call the CFG scale alpha. Then you have a velocity field v hat TT alpha. And then you just add another integral here over alpha. And then x hat depends on alpha. So you just make everything depend on alpha. And then you just have this model that has a CFG scale as input. This is described in the main text and the appendix of the paper if you want to see the details.
Thank you very much.
All right, then I think the remaining two hands are old hands, but oh, nope, never mind.
I have a new question if there's time.
Let's go.
Yeah, I have time.
I'm wondering if you make this for discrete spaces, what breaks and perhaps what doesn't break?
The $1 million question. Yeah, we'd all love flow maps for language, right? Yeah, we'd all be billionaires if we had that. I don't know. We're looking at it. It's hard. It's quite different than the continuous space, and I think there's a lot of work that needs to be done there. I think it's a very exciting direction, and a number of my grad students are like super stoked about it and have gotten me quite interested in this. I also think Michael is kind of working on related things. But yeah, it's pretty open at this point. I don't think anybody really knows how to do it.
I see. There's not like the first equation where one assumption breaks of this.
Everything breaks, like
Okay.
level 0 breaks. I mean, it's because like you have like the way discrete models are typically formulated is in terms of a continuous time markup chain, right? And that continuous markup chain is stochastic. I don't really know how to do something deterministic for discrete models. Certainly the typical formulations of discrete diffusion, discrete flow matching, it's fundamentally stochastic when you're sampling. But what I really used here continually is that the ODE is deterministic, and so it defines a unique map from any given XS to another XT, and so I can learn that with a map. For discrete, you would something like a stochastic flow map, and it's really a bit unclear mathematically what that even means. It's a much harder object is actually an infinite dimensional object. And so it gets quite nasty, quite.
I see. Thank you.
Okay, then I think now we have reached the end of the questions. With that, Niklas, would you want to say any last words before we call it a day?
I think that's pretty much it. Yeah, thanks everybody for attending, asking the questions. I really appreciated it. And hopefully you can try out these methods on your own problems. If anybody is interested in applying the Lagrangian approach to some interesting challenge, feel free to send me an email. I'm happy to provide some feedback. And all the code for this is online. I put a lot of effort into making like a very nice repository where it's easy to use, it's easy to replicate the experiments, and you have implementations of everything that we've done here. So if you want to use that, also please don't hesitate to reach out if you're having trouble. And as Hannah said at the start, I am indeed recruiting PhD students and postdocs for the next cycle. So if anyone's interested, feel free to reach out.
Okay, then thanks, Nick. See you around and nice work. Enjoy.